welcome to this lesson on probability counting principles part 1. Let's have a look at counting with identical objects. So up to this point, what we saw when we were counting with or without repetition was that sometimes objects could be the same and sometimes objects could be unique. So for example, for the pin number example, in each of the 4 different slots that you can pick 10 digits from each set, those numbers 0 through 9 were the same as the second set, the third set, and the fourth set. So they were identical objects in each set. And then for the example of how many people can we arrange in a straight line to take a photo, people are unique. Each person is different from the next person. So those were different mathematical objects in a sense. So let us consider the following scenario. We are given the word book, B-O-O-K. And I've colored them specifically like this. There are 2 O's, 1 B and 1 K in that word book. So there's a repetition of the letter O. Okay, so that means we say that same letters are considered to be identical. Okay, so those 2 O's are identical to each other. Then we have the following number of arrangements, different arrangements, I should say. So you could start off with the word book. Okay, then you could write boko or biku or obok or oboko. Okay, it doesn't have to be actual English words, but we're just looking at the arrangements that we can order around. Now, when I do this, the number of different arrangements I arrive at are 12 different arrangements. So notice that something like OOBK. Okay, so that's this one here. This one here. Okay, that one is indistinguishable, so it's considered the same as this one here, OOBK. They look like they're the same, but can you see the 2 O's have been swapped around? Okay, but we consider those 2 O's in those 2 different places to be the same identical letter, so OOBK and OOBK here are considered the same object, so we don't count it twice. Okay. Even though I've colored the letters different, it's just to illustrate that you could swap the 2 O's around, but still end up with the same word, OOBK and OOBK. These are identical words. So mathematically, we can see that the total number of arrangements is 4 factorial. So that's the number of letters that we have. So we can arrange them in 4 factorial ways. But then we divide out that repetition of 2 factorial, the 2 O's, and we get 12. So we can verify that. So 4 factorial over 2 factorial, that's 4 times 3 times 2 times 1, over 2 factorial is 2 times 1. 2's will divide, 1's will divide, and you're left with 4 times 3, which is 12. So this is due to the fact that there's a repetition of 2 O's that are considered identical. So we can generalize that counting scenario when we have multiple identical objects in a given structure. So this is an extension of the fundamental counting principle with multiple identical repetitions. So, example, you could have a word like this, let's say the word ant, eater, something like that, right? Then you've got 2 A's, and you've got 2 E's, and you've got 2 T's. So there's multiple identical repetitions, 2 A's, 2 T's, 2 E's. So if we have n objects, of which there are n1 of the same object A1, n2 of the same object A2, and so up to nk of the same object AK, then the total number of different arrangements of n is given by the total number n factorial of ways you can arrange all n letters or n objects, and dividing out all the repetitions. So n1 factorial times n2 factorial all the way up to nk factorial. So for example, in the word anteater, there are 3, 4, 5, 6, 7, 8. So there are 8 objects, 8 letters. And we have 2 A's, we have 2 T's, and we have 2 E's. So the number of unique ways we can arrange the letters of the word anteater to make other words is 8 factorial divided by 2 factorial times 2 factorial times 2 factorial. Okay, so just to show you on your calculator where the factorial notation is, if you don't want to work it out using longhand notation. So I've got my fraction, so it's 8. Then above this x inverse button, if you press Shift X inverse, you'll get the exclamation, which is the factorial notation, divided by 2 factorial times 2 factorial times 2 factorial. That gives you 5040. Okay, so there are 5040 different ways that we can arrange the letters of the word anteater to make a completely different word. It doesn't have to be a word that makes sense, but a word that is unique. Okay, so that is counting with identical objects. I'll see you in the next one.